So our next problem is number 25. And this is sort of a fun problem because it's a real-world problem. Find the angular velocity, or omega, for each of the following, and for number 25, it's the hour hand of a clock. The hour hand of a clock. So let's draw ourselves a picture. I always like to draw a picture. Kind of makes things much clearer and much more fun. So here we go. I'm drawing my clock. Okay, and drawing. Maybe a little more than I need to draw, but it's still fun. Okay, so let's say that we're going from midnight. Let's just draw the hour hand. And then an hour later, it's 1 a.m. Okay, so in an hour, the hour hand travels this amount. Okay, and the question is, what is, since we're looking for angular momentum, what is the angle that the hour hand travels from here to here? Well, a full circle is 360 degrees, right? Or 2 pi, right? So 2 pi radians is the full circle, and this is what portion of the circle? Well, from 12 to 1, 1 to 2, 2 to 3, you count them up, they're 12 equally spaced angles, right? If we're going to 2, to 3, to 4, to 5, etc., we would be dividing this into 12 equal angles. So the angle that the hour hand travels in 1 hour is 1/12 of 2 pi, or we can say that's also pi over 6 radians. That's in an hour. So therefore, the angular velocity would be pi over 6 radians per hour. And that is the answer to 25. Let's look at, next problem is 32. We're told that we have to find v, which is the linear velocity. And the problem is that we have a point on a tire. Try to draw a circle. Okay, a point on a tire. The radius of the tire is 18 centimeters. And it's rotating 35 times per minute. Okay, 35 times a minute. And what is the linear velocity? Okay, so think about it. We have a very simple formula for linear velocity that is rate times time equals distance, right? Where we're looking for the rate. So this has nothing to do with what we learned about circles, but it's always true. So if we were looking for the rate, or the linear velocity, that would be the same thing as distance divided by time. Well, how does this help us at all? Well, let's try to figure that out. What is the distance that a point on the circle here would travel in a minute? I say a minute because that's the unit time we're given. We're given that this is rotating 35 times per minute. So, well, how far would one rotation take a point? That would just be the circumference, right? So the distance that one single revolution would cause this point to go 2 pi r distance, where r is 18. We'll plug that in a moment. But we know that every minute, this is happening 35 times. Okay, so the total distance that this point is traveling is whatever the circumference is times 35, because it's going around and around and around per minute. Okay, so now let's go ahead and let's plug r in, which is 18. So we get that the rate, or the linear velocity, is 2 pi times 18 rather, which is the radius, times 35 per minute. And let's get our calculator out and see what that comes out to be. So we've got 2 times 18 times 35, and altogether that gives us 1260 pi. And what is our unit of distance? It's centimeters. And what is our time per minute? So that is the answer for 32. It would be 1260 pi centimeters per minute. And now let's go on to problem 35. So 35 is another fun problem, and I find problems fun when they have to do with real life. So let's take a look at problem 35, the speed of a bicycle. the tires of a bicycle, and again I'm going to draw a circle here, have radius of 13 inches. And they're turning at a rate of 200 revolutions per minute. How fast is the bicycle traveling in miles per hour? Okay, so we're given inches and minutes as units originally, and somehow we're going to have to end up with miles and hours. Okay, so we're just going to make a note of this. Okay, so we're going to have to do that at some point. But let's start with this, and let's ask ourselves, can we get a distance? And then can we get a velocity? So the tires are turning 200 revolutions per minute, and in each revolution that the tire turns, it's going one circumference. Well, this is very similar in some ways to the problem we just did. So our distance, okay, again we have rate times time equals distance, and if we're solving for rate, we have distance over time. So the total amount of distance that's being traveled by this point, which is the same thing as how fast the bike is moving, is going to be 2 pi r, where r is going to be 13, times 200 revolutions. That's the total distance that this tire is traveling, and that is going to be per minute. And let's plug in r here is radius. I probably should use v for velocity since I've already got an r going. So let's go ahead and plug in 2 pi times radius is 13 inches, okay, O times 200 per minute. So that is our angular velocity. So in one sense, we're sort of done. We've got the answer, but we don't have it in the proper units. We've got it in inches and minutes instead of miles and hours. So let's actually take this answer, put it on a new line over here, 2 pi times 13 inches times 200. I'm not even going to simplify it yet, per minute. And what I want to do is I want to multiply it by several factors that are going to change inches to minutes and miles to hours. So the easier one to do is, inches, what did I just say? Inches to miles and minutes to hours, okay? See, so I'm sorry, I kind of said something silly there. So we've got to go from minutes to hours, and that's the easier one to do first. So we've got minutes as a unit in the denominator here, so we're now going to go ahead and put minutes in the numerator here and hours in the denominator here. We've got 60 minutes per hour. So the value of this ratio is essentially 1, because this is 60 minutes equals 1 hour. But by multiplying by 60 minutes over an hour, we're going to be able to cancel out the minutes, and we're going to be left with the hours in the denominator, which is what we want. Excuse me. I'm so sorry. Okay, so that takes care of our minutes to hours, but we've got to somehow end up with miles in the numerator instead of inches in the numerator. So we're going to have to remember some more identities that will help us to cancel inches into miles. Well, there are there's 1 foot per 12 inches. Okay, and when we multiply by this, we're going to cancel out inches in the denominator with inches in the numerator and replace it by feet in the numerator. And so now we also can multiply this further by 1 mile per 5,280 feet. Okay, and that will cancel out the feet and leave us with the mile. So this is a way you could do unit conversions. So let's go ahead and actually cancel out minutes here, cancel out inches, cancel out our units first, and our feet. So now we are finally left with miles per hour. And all we have to do is multiply everything out and see what we get. So let's go ahead and multiply 2 pi by 13 by 60, and then divide the whole thing by 12 times 5,280, and let's see what we get. So we've got 2 times pi times 13 times 200 times 60. Okay, that gives us everything that was in the numerator. 2 pi, 13, 260. Okay, all divided by, put this in parentheses, 12 times 5280. And let's see what we get. So we get 15.4699. Okay, and that basically means our linear velocity is 15.46996. I'm going to take it to a whole bunch of decimal places, and we'll deal with that in a moment. But our units now are miles per hour, because that's what we've got left, and that's pretty good. That's what we wanted. But we've got the issue of significant digits here, okay? And we don't have to worry about significant digits so much in terms of dealing with these identities that we're using, but we do have to worry about it when we're talking about, for example, 13, 200 revolutions per minute. And it's sort of a bit of a value judgment, but if we could probably justify rounding off to either 2 or 3 significant digits. Okay, I think in some ways the 2 significant digit is a little more compelling to me, but let's go. I know the book was going with 3 significant digits, so let's go ahead and round off to 3 significant digits, and that would give us 55.5 miles per hour, which is the book's answer. I might actually say that the slightly more correct answer might just be 15. If you notice, 0.46 would not round up to 16, but it would be 15 miles per hour. I think, given the significant digits, I think we should probably only be rounding off to 2 places, but that's just my opinion. As long as you know how to do this problem and how we got this answer, that's the major thing here.